Good afternoon. It is a great pleasure to introduce our speaker, the speaker of today, Professor Robert Shelton, who is currently the president of the GMT organization. Dr. Shelton made his undergraduate studies at Stanford University, and he got his PhD at University of California at San Diego. His specialty is condensed matter. He's an experimental physicist. And he worked as an experimental physicist at Iowa State University and the University of California, Davis. And then he became the provost of the University of North Carolina at Chapel Hill. At that time, I met him for the first time when we had the first light of the SOAR telescope. I was the president of the SOAR board, and he was the provost of one of the partners. So we went both to the inauguration, to the first light of the SOAR telescope. Of course, we are both 14 years younger than we are now. After that, he became president of the University of Arizona. The University of Arizona is well known for astronomers. The University of Arizona is an important partner of the GMT, and where the mirrors are being made at the Mirror Lab of the University of Arizona. After the University of Arizona, he went to be president of Research Corporation, which is an important corporation that provides grants to young scientists with private money. And currently he is our president. He became president of GMTO about a year and a half ago, more or less. And today he will talk to us about the program, the project, and the current status.
Thank you. Let me test the volume. It's okay? People in the back cannot fall asleep as easily? Okay. João, thank you for the introduction. I must say it's a great joy to be here. This is my first time in Brazil. It is an extraordinary country, as you know infinitely better than I. But here I am in Sao Paulo, one of the world's great cities. And before coming here, I took advantage of the trip to spend a couple of days at the Foz do Iguaçu, Iguaçu Falls. So one of the wonders of the world, no doubt about that. They proclaim that on all of the placards, justifiably so. And my joy now is to tell you about what I think will become another one, at least of the man-made wonders of the world, the Giant Magellan Telescope. I do have one request, and that is feel free to interrupt and ask questions as I go through the presentation. I guess I have a second request too. As João said, I'm a condensed matter physicist, not an astronomer. So if you ask any difficult astronomy questions, I will defer them to my host, João and Claudia, who have been extraordinarily gracious in setting up all of these meetings and discussions. So thank you for having us here. The title says it all. Let's move on. Let's move on. Make sure I do this right. Here's a rough outline. Of course, I want to talk about how we're organized, the key roles that players occupy, including FAPESPA as one of our key partners. But then I want to get right into the science and talk about where we are, because this is an extraordinarily exciting time for GMT. You know how these projects go. There's a lot of thought that goes into them for a while. There's a lot of planning. There's a lot of paperwork. There's a lot of documents that are drawn up. And then, oh, finally, something starts to materialize. Finally, you level off the top of the mountain to provide a space for the telescope. Finally, you get water and power and internet. And finally, you start to see some visible manifestations of this incredible project. That's where we are right now. We are starting to see visible manifestations of this project that has everybody excited. So I'll talk about that. And I also want to talk about how we constantly review ourselves, constantly get feedback from the broader astronomy community to make sure we stay on on task. This is a partnership. We have 12 partners. We call them founders, 4 of them international, 2 from the country of Australia, 1 from South Korea, and of course here in the state of Sao Paulo, FAPESP. We have 8 universities or institutions in the U.S., from the Northeast, Harvard, down the East Coast, Carnegie Science, and then of course Texas and the great Southwest, and where I spent a number of my years at the University of Arizona. So this is the partnership. We are welcoming new partners. In fact, the sister institution to the U of A, Arizona State University, just joined us about 8 months ago. Let's talk about the organization. This, contrary to popular belief, this is not of Zhao and me when we were at the SOAR telescope. Here is a composite photograph of our board of directors. Each of our founders has 1 or more members of the board. You can see Claudia there. Standing next to Walter Massey with the blue tie, he is the chair of our board. And the only outlier here is me. I'm not a member of the board, but they welcomed me into this photo. This was taken at the last board meeting we had in Pasadena at the Langham Hotel. This is an older photo of our staff. What I like about this photo is the tremendous diversity that it shows. We have, of course, colleagues who come to us from Brazil, from Chile, from Korea, from Japan, from many other institutions and countries. The math is not incorrect here. We have 108 full-time equivalents, but a lot more than 108 people, and that's because many of them are over here, distributed not just at our offices here in the US, nor in Chile, but contracts and people that we work with. So about 108 full-time equivalents. There is, however, a great omission in this photo because of the time it was taken, and that is my colleague who's with me here today. Jennifer Eccles is our Vice President for Development. That means she helps me raise money. She comes to us from 10 years at the University of Southern California, which is, as you know, a very prominent private university in the U.S. Jennifer, maybe just stand up and say hi, or say hi. Okay. And here's just a brief set of very key activities where we have drawn potential donors to come and visit visit the project. Okay, I mentioned that we have consistently reviewed ourselves to make sure that we aren't doing better than we think we are, to make sure that we're on schedule. And I'm having trouble. There we go. This is our standing review board. I'm sure those of you in astronomy recognize many of these names. Sidney Wolf is the chair, Mark Reichenader. The other thing I would point out to you is the variety of institutions that we draw on to populate this review board, including the 30-meter telescope. Some people think of them as our competitor. That's not really the case, and I'll mention that in greater detail later on when I tell you how we are collaborating with the 30-meter telescope. But these are people that give us a tremendous amount of time, and they are, if you know any of these people, you know they are very candid, and they give clear reviews, either positive or negative, as we go forward. To give you one other sense of how often we review ourselves, here is a list of recent reviews, 2017 into 2018, reviews of the subsystems. I don't need to read this, you can. And more recently, review of the entire system that we have, our business practice review. And really a critical one that just finished in May was the integrated baseline review. That was the totality of what we're doing. The team came in for multiple days, and in the end we got a very positive review that now allows us to move into something cleverly called the earned value management system. So you know if you spend $1, whether you're getting the dollar's worth that you expected out of it or not. So we are an open book to what is going on here, and I think that's really critical for a project of this size and this complexity. Okay, that's all of the critical, maybe not so exciting, but critical set of governance and paperwork out of the way. Let me talk a little bit about the science now. And here is where I'm starting to get out of my depth very quickly. We have a science advisory committee, a hard-working group that's been in effect since the beginning, and most recently under the leadership of Rebecca Bernstein, who is our project scientist. She comes to us from Carnegie. Before that, she was at UC Santa Cruz. Before that, at Michigan. Under the leadership of Rebecca, this Science Advisory Committee has just finished, I think it was this last week, just finished the update of the science book. What is the science book? Well, it has introduction and then 8 chapters, all talking about the exciting, extraordinary science that will be accessible to the Giant Magellan Telescope, and accessible only to a telescope of that size. You can see here there's a lot of emphasis on galaxies, a lot of emphasis on stars, star formation, and of course really fundamental esoteric questions, cosmology, first light reionization. Claudia, I don't know that we've yet sent that out to the board members, have we? Yes. Okay, you have that. Good, at least in electronic form. The brilliance of this science book is not just the content, but the way it's presented. These are the opening pages of each of the 9 chapters. You can see that they're visually compelling. That's an advantage astronomy has over probably all other disciplines. And inside there are sections that are organized, color-coded, so the general public can read that. That's important for us when we go to Congress. That's important for us when we go to independent donors who might want to support the GMT. Then there's another section that talks about the key questions that the GMT will pose and try to answer. And then finally, there's the real nitty-gritty kind of science that all of you can read and understand and savor when you read this science book. So we just got it done. It's just been sent electronically, and I'm sure you can find it on our website very soon, on a website coming to you. So it's just a brilliant piece of work. It's about, I think it's about 220 pages long. Here are some slides that illustrate the kind of science that we think GMT will go after that can't be done before. So here's an illustration of this disk galaxy and the kind of resolution you can get. This is what you see on the right-hand side is what you see with an 8 meter with adaptive optics. And then you can move ahead and see what we anticipate getting with the GMT 25 meter with adaptive optics. Up here you have the scale 0.5 arc seconds. Another example is probing the galaxy structure. Again, doing comparisons with known instrumentation, James Webb, Gemini 8 meter. Here's the simulation, and this is what we expect from GMTA and the K-band. Again, the scale up here. So it's really going to be a huge step forward. Black hole at the center of the galaxy, VLT with adaptive optics, and now you see GMT with adaptive optics. Of course, we still have to build the thing, right? But you see this kind, and it's really inspirational. It's inspirational not only to knowledgeable astronomers, but to people like me, scientists with a great interest in astronomy. I want to spend some time on this topic here, because this has come up recently. The GMT and the TMT will be built in Hawaii, they hope, have been both progressing along. I think we are considerably farther along than they are because we don't have our site problems. But that said, they're both big projects that involve the U.S. astronomy community. Not only the U.S. astronomy community, but certainly the U.S. astronomy community. I think you're familiar with TMT. That is Caltech, the University of California, and then some countries, Canada, Japan, China, India. And so for a long time, the question that both of these organizations has had is what role, what kind of funding can we expect from the U.S. government? And the U.S. government has said, well, you know, unless you two cooperate, we can't make a choice. We love you both, but we can't make a choice. And so just recently, in the last month, there's been a meeting of the minds and a meeting of the bodies of the leadership of TMT. Here's Ed Stone, who used to be the director of the Jet Propulsion Lab. Here's Rebecca, Mike Bolte from Santa Cruz, and the GMT. And so this was the first meeting that we had in our offices in Pasadena. We've had another meeting at their offices in Pasadena to talk about how we come together to utilize vehicles like that science book that is just GMT, how we come together to talk about the key science projects that can occur with an extremely large telescope in the northern hemisphere and one in the southern hemisphere. It's a unique partnership that I think will be compelling to the decadal survey that's due in 2020. Okay? So the process is come together, talk about key science projects, document this for the decadal survey, be number one ranked in the decadal survey, which then gives the U.S. federal government, in the persona of the National Science Foundation, an opportunity to put money into both projects. In this kind of money, we're talking 350 or 400 million US dollars into each project. So this is a significant effort on our part. It's a significant effort that we have created a decadal survey working group. Here's some names. Taft Armandroff, he is the director of McDonnell Observatory in Texas, and he's on the faculty. Rebecca, I mentioned her earlier. She is our project scientist. Buell Januzzi heads up the Stewart Observatory at the University of Arizona. Patrick McCarthy is our vice president at GMTO and an astronomer of decades of experience, comes to us from Carnegie. And then, of course, Claudia here is our international representative. And I can tell you, you are extraordinarily well represented by Claudia's presence. The goal here is to make sure that our unique structure with our founders, with our partners, continues to be honored as we seek funds from the federal government. Okay? The founders, including FAPESP, have already put in or made legal commitments in the next 2 years for over $500 million, so that's significant. If we are successful, and I'm sure we will be, with the National Science Foundation, that would be another $400 million. So that is a significant fraction of what we're doing here. So this is the team, and you have your very own representative right here who is highly engaged. Okay, let's talk a little bit about the telescope. This is a graph that Pat McCarthy, I should have said that. These figures were all put together by Pat McCarthy. I just mentioned him. He's our vice president. He's been with the project for over 12 years. He knows more about the history of it than all the rest of us put together. And he always insists that I show this graph. This, of course, shows the size of the aperture of the telescope, okay, over time. And it's plotted on a semi-log plot. And of course, anything you plot on a semi-log plot is linear. That's the virtue of a semi-log plot. And it shows the development that you get a doubling about every 30 years. Okay. And so it's been roughly 30 years since you had telescopes like Keck at 10 meters. By the time we're on Sky in 2024, okay, that's about the right time. And then here we are with GMP. I'm sure each of you know better than I the kinds of discoveries that have occurred each time you had a significant growth in the aperture. You know, expansion of the universe, other hypotheses that had to be confirmed with a telescope that had greater light collecting capabilities. Okay. I'm going to talk now about a few of the key components and where we are. As I said at the beginning, this is really an extraordinarily exciting time because of the visual value that we have, the progress that we're making on the technical side. That's manifested in one way, maybe in one highly visible way, by the telescope mount. That's what we're talking about here. You can see it's almost 50 meters high. It holds all of the mirrors. It holds all of the instruments. Of course, the secondary mirrors, it has to rotate, it has to tip. We started last year with a request for proposals, and we got 5 bids from international firms, all of whom have great experience in building this kind of apparatus. Experience, whether it's with LSST, with DKIST, with Subaru. 5 bids. We took those through a review process, and we selected 2 of them, 2 vendor teams. Those two vendor teams were given design build contracts for a 6-month period. And they're engaged in those now. We're working closely with them. One of them is out of Germany, MT Mechatronics, and they have Ingersoll Rand in the US, where they would build it. The other is EDOM out of Spain, also with a US partner. The US partnership had nothing to do with the decision. It's just that the review led us to these two. They're very different in terms of their experience, and we wanted that kind of variation in the two that we chose. So right now they're in the middle of this, says 6-month, it'll probably be 8-month design. We expect by the end of this calendar year to have their firm final design and bid to build it. And then we have to choose one or the other for a contract that's probably $100 million. So this is the single largest item that we will procure. And the good news is we are going to be prepared to down select this in 2018 and take it to our board of directors for approval at their February 2019 board meeting. Here's an example of what it looks like in a different profile. I wanted to put this up because it just illustrates one of the many complicating factors in designing this, and that has to do with the fact that Chile is in a seismically very active part of the world. That's an understatement, I think. Fortunately for us, or I don't know, maybe unfortunately, California is also in a very seismically active portion of the world. And so we have a lot of examples of how buildings have been designed and redesigned in California to deal with this. And what we decided on is this friction pendulum, where this is attached to the ground, this part here goes to the building, and as there's movement, it sways back and forth, and eventually equilibrium brings it back to this point. These are used throughout California. In fact, interestingly, the president of the University of Texas, one of our partners, is a seismic engineer. And when I was talking with him about this, he then gave me a lesson on it from his time when he was at UC Berkeley. You can see here, we really get into the work. This is on the Pasadena City Hall complex, where they have 240 of these friction pendulums. This is down in taking a picture of this. This is why I have younger staff to go and see how these operate. You can see them on the parking garage at the Burbank Airport. They're all over. So it's a proven technology, and they will be here to isolate the pier from the ground. The AGWS, Acquisition Guiding and Wavefront Sensing, keeps the telescope pointed and tracked. This is moving along very nicely. One of the more complicated instrumentations that we're going to put together. We are already in the 3rd generation, and one of the beauties of our location and our partnership with Carnegie is we can test a lot of these things in situ at the Magellan on the Magellan Clay Telescope, which is just the next mountain over. Secondary mirrors. The status of the M2 mirrors is there's a detailed study underway with Ad Optica in Italy. Just like we have 7 primary mirrors, we have 7 secondary mirrors, and of course the structure that holds and allows them to be focused. These are going to eventually be adaptive optic mirrors, of course. Okay, speaking of optics, let's talk about optics. When I was president at the University of Arizona is when we started polishing the first off-axis mirror. First off-axis mirror. Never been done before. They had made 8-meter mirrors, 8.4-meter mirrors that were, nice concave, but they'd never done an off-axis mirror before. And I remember talking with the then leader of Carnegie, Wendy Friedman, and we both discussed how concerned we were about whether we could do this. Because if you couldn't make that mirror, all bets are off. You might as well stop there. Well, Arizona was successful. And I'll show you again where it is. Scale, the 4th mirror, this is the hole in the 4th mirror, is the center mirror is the size of the Hubble Space Telescope mirror. So that's the 2-meter mirror. Another example is JWST, the James Webb. This is what the Webb series of mirrors will look like in its size compared to one of the GMT mirrors. Okay. So here we go. Let's talk a little bit about where we are. The first mirror is done, completed. It was put in a box, a $1 million box, and taken from the, nothing is cheap when you build a telescope this size, taken from the Mir lab and then put down in the private airport hangar down at the Tucson airport. Okay. The second Mir, the polishing there has gone much more rapidly. I'll have a graph showing that later on. It is almost complete. It should be completed maybe by the end of the year, certainly by January or February. It will be put in a box and taken down to the airport and stored. Third Mir has all of the support on the back. The back side is finished. As soon as this Mir, the second Mir, is done, this Mir goes into the polishing machine. Fourth Mir, we're ready to put the supports on the back side. I don't know if you can see it. This is the hole here. That's 2 meters there. Okay. Fifth Mir, we had a spectacular event last November for the casting of the fifth Mir. You can see gentlemen standing on it. It was very successful. It came out of the oven, and it was probably the most successful mirror cast by the Mir Lab at the University of Arizona to date. Equally importantly, because there are a lot of potential showstoppers, equally importantly, we have all the glass in hand for 6 and 7. Why is that important? Well, there's only one place in the world that makes this glass. It's E7 borosilicate low expansion glass out of Japan, Ohara. We buy 20 tons of this glass for each mirror. You use about 18 tons in the end, but you need some spares. And so we didn't want to be left without a supplier should O'Hara decide not to do this anymore. So we have all the glass in hand. It's in small individual boxes stored somewhere in Tucson. So we feel good that we've reduced any risk to completing the mirrors. Here's a little video of moving the mirror last fall. Again, the mirror weighs about 17 tons when it's done. The box itself is very robust, very secure. It has a lot of cushioning and support. It's made of steel, so if anybody shoots at it, it won't harm the mirror. I'm not making that up. And it weighs about another 20 tons. So you're moving about 40 tons. There's a specialized group that does that, obviously. You can see here now the mirror is in this mirror casing. It's coming over to the door to go out. This is all done under the football. That's a U.S. football stadium at the University of Arizona in the Richard Karras Mirror Laboratory. I'm not responsible for the music. This was done, of course, in the middle of night so that it could be transported to the airport about 10 kilometers away at 2 or 3 o'clock in the morning. An understatement, oversized load. You can see they have to balance it. It gets balanced on this trailer with 48 independently sizable, independently suspended wheels. This is one of the assignments I sent my vice president to oversee. So there it goes down the road. They are very proud of that, justifiably so. Okay, and this is showing it, everything is in, this is real time, this is not slow-mo. Going into the hangar. We spent a long time finding the right place to store this. It gets very warm in Tucson, 42, 43, 44 degrees, and so you want to make sure that you don't have giant swings in temperature. I'm spending some time on this because you're going to see another mirror next to it. You'll recognize that. Now there it is. So here we are up on these platforms, and here's the LSST mirror, which should be departing soon to be installed at the Large Synoptic Survey Telescope, which gives us room for our second mirror. Okay. So the mirrors we feel really good about, where they are, how quickly the polishing is converging on the second mirror. And here you can see the fine polisher. You can see when it started, this is the end of January in 2018, this line here. And this is the surface error in nanometers. Okay? And we're trying to get down to 20 nanometers, RMS. The points here are the actual data. This is now about July 15th, July 10th of this year, and you can see it's converging faster than even the most optimistic line, and that's because they're learning, right? The most optimistic line, most likely, and pessimistic were based on the first mirror. So this is really exciting for us. This could save us 6, 7, 8 months. Okay? So that's very good news. So the message here is the mirrors are doing well. This shows the loading of the glass for the segment 5. You can see these chunks. They're about a third of a meter on a side. They're irregular. They're all tested optically before they're put in. And then they go into the mold, and this furnace, remember this is 8.4 meters in diameter, is fired up. And you cool it down very slowly. There you see it before cooling. You can see all the individual chunks in the furnace frame, and here's how it comes out with the ceramic underpinning that'll be washed out later on, so you wind up with a fairly lightweight mirror, only 17 tons.
So a quick question.
Please.
Why does the furnace need to spin?
You spin it so you get the centripetal force that gives you a rough parabolic shape, and for the center mirror, that's almost where you need to be. And then you polish down to get the final shape that you need. So you get roughly what you want. And it's cooled very slowly, of course, so you don't have any stresses in the glass. Here you can see the load spreaders on segment 5. They put these on here. They're held on by suction cups, and then they pick it up and turn it vertically so they can wash out all the ceramic that you don't need. It's a rather frightening time, but it works. Just another shot of the. This is the mirror 5. Okay, we were looking at the top earlier. Let's talk a little bit about the dome and the site, because there's a tremendous amount going on there now. I think you all know where it is, but let me remind me at least. We are here right between regions 3 and 4 in Chile, just a little bit north of the LSST, a little bit north of SOAR, and south of ALMA and up where the ESO is building their telescope. It's a terrific site. You can see it here. This was before we started work. The Magellans, the 2.6.5 here, the older one, the DuPont 2.4. This is the road that comes up, and then you have a decision here. You go over to Magellan, or you come around this way and up the back to the site of the GMT. Okay. It's a tremendous site. Really, we are so indebted to Carnegie for having purchased this land, hundreds and hundreds of hectares, in the late 1960s. Okay, we've seen that the scene has remained constant and outstanding for decades. One measure of it here is the scene quality at 50% level at a certain frequency. You can see what it's like at the Magellan site. This is Las Campanas, is where we will be. Here's the Magellan site. You can see that it is just extraordinary. This, in case you can't read, this is a scene in arc seconds. Okay. So we are happy about where we are. This is a sketch to orient you. You come up the Pan American Highway. Here's where you make that decision going over to the Magellan or coming around the back of the mountain to the site for the GMT. This is support site 1 here, where we'll have machine work, tooling, able to make repairs. This is support site 2, which you'll see is complete in the sense of the buildings. You'll see a residence hall for observers and for visitors, cafeteria, recreation area, and a residence area for workers. Up at the top site, this building is in. This is again for construction, and all of the rest of this is about ready to be started. Okay. Another artist's rendition. Obviously the telescope. Down here is a utility support building, getting it down and away in terms of vibration, in terms of wind flow. And then this building B would be where you recoat the mirrors. Sadly, they have to come out periodically and get recoated. and this is for housing workers. I tell people that aren't familiar with this, this is the size of a 22-story building. They go, oh, well, we see a lot of 22-story buildings, but it has to rotate. And you can get the scale here, noticing the cars. Okay. So, hope I didn't, okay. I'm going to have a drone fly over here. This is current. This was just last month. Again, I mentioned here residence for observers. Here's cafeteria, recreation area. This can house 250 workers in triples. The observers have singles. Water supply here. This is you can see how this has been excavated back to provide a flat area for the support site 1. The road is in, even a car driving on it. We have our guardrails that are in. That's very important. Coming on up, you can see the two stanchions here where we've taken a lot of data on weather conditions. Coming up, this is the one building that's been on the site for some time. Again, it's to house construction activity and workers. We originally thought to have the telescope at this end of the mesa that we created, but after doing a lot of studies, it was decided that this end is optimal. You could put a second GMT here, but I don't think that's in the cards right now. As I said, you have road, you have water, you have power, you have internet. All of that's available up here. This is the site, and you can see the very beginnings of the equipment to start the hard rock excavation. Core samples were taken to make sure this is where we wanted to be, but now we have to get serious and start excavating the site. This still shows the size of the foundation for the telescope mount, and this is the outer diameter of the dome, about 56 meters. So everything is big. This is one of the most important developments. You might think it's strange that I'm saying that when I've been focusing on the really critical elements for an observatory, namely the mirrors, right? The telescope mount, the enclosure. But this is something that tells the world we are really serious. We have started excavation on July 25th. Excavation of the telescope pier, the enclosure foundations, the coating chamber, and the support buildings. And you can see here some of the equipment that's up there, drills, impact hammers. You want to make sure you drill, but you don't want to fracture the rock. So it has to be done very well. The group that we hired to do this after competitive bidding, we gave them till next April. Right now, they're saying they think they'll be done in December. So what I'm dealing with, what Jennifer is dealing with, what our whole organization is dealing with, we have this tremendous progress that's coming about through the technological advances, whether they are overt like this or behind the scenes like our IRB review demonstrated. And we just need to be sure we raise money in time to support all of that. So it's a good challenge to have. This is, I think, a sequence that is important for folks here in Brazil, for the possibility of getting industry in Brazil involved in this activity. This activity is, of course, constructing the enclosure. You can see here there are a number of stages. This gives you a sense of the timeline. It takes a while. Okay. We expect to issue the request for proposals for the concrete package early next year and make the award a few months after that. That's called Stage 2. Stage 1 was the hard rock excavation. Stage 3 involves the steel. And I know that Brazilian industry has experience in this from SOAR. So that RFP is going to be released in a little over a year. And about 7 months, 8 months after that, we would award the contract. And then there are a whole lot of parts and pieces that have to go into this. Cranes, windscreen. Again, in September 2019, a little bit ahead of this, so that the contract is awarded at a compatible time for both the steel package and the mechanisms that have to interface to that. And then finally, the stage 5 here in 2020, they'll be awarded. So it seems like this is a ways off, but it's really not. It comes up very quickly. I mentioned earlier the size of our team. We have 108 people. That's a pretty small team to be doing all this, because most of them are systems engineers, and they've got to bird dog and understand completely all of the proposals that come in. You have to treat them independently and make sure that there's no crossover in information. So when you choose one, it's a legitimate selection. Talk a little bit about scientific instruments. Okay. I learned from the first time I got involved with an observatory, I was on the Keck board, that astronomers always want more instruments. And the instruments always cost more than you can imagine because they're really complicated and nobody's ever done it before. So those are legitimate requests. How do you accommodate them then? Okay. The first ones we're looking at here is GCLEF, and I think a number of you know Anders St. Georgi. He is the PI. And GMAX with Darren DePoy at Texas A&M. GCLEF is in the stage of a final design, and they're getting specialty glass, and that is an instrument we want to have available for first light. You know, Rebecca Bernstein, the project scientist, always reminds me that the telescope just collects light. It's the instruments that do the science. So we have to have instruments ready to go at first light. GMAX is still in the conceptual design. There's a lot more to be done in that regard, so a lot more opportunity. And I note here that, as I heard earlier today, a number of scientists and engineers from Brazil are involved with both of these. Maybe to a higher degree here because of the timing than over here. But we really appreciate that expertise coming and joining us on these instruments. GMT NIRS, that's being guided out of Dan Jaffe, UT Austin, and then GM-TIFFs out of Australia National University. Again, the status of these, they're pretty early, preliminary design. But again, we have some contributions and some critical role being played by some Brazilian scientists and engineers in GMT NIRS. Okay, we appreciate that. Okay, so this is the summary. I haven't been watching the time carefully enough, maybe. This is the summary. If there's nothing else to be taken away from this talk, it's that we are making incredible progress. It's not me, it's the team, it's the engineers, it's the scientists, it's the support people, it's the financial folks. We are now at a stage where we are visibly, clearly going to succeed. You know, until you level off the summit, until you have something physical to show people, until you have great partners signed up, people can always be skeptical. There's no reason to be skeptical now. Okay? We have resolved the potential risk that you'd have on the primary mirrors. We not only know that the mirror lab can polish them to the 20 nanometer RMS resolution that you need, but also that we have all of the glass we need for the 7 mirrors. Okay? We know that we're moving ahead on the mount. The single most complicated item we have. We've got through the initial review of the 5 companies that bid, major companies worldwide. I mean, when we told Melco, Mitsubishi Electric Company, that they were not chosen, they sent a team of about 8 people over to understand why. They really wanted the bid. Okay? It was simple. They were just too expensive. Construction work on the site is underway. Jennifer can back me up on this, but it's amazing how many people you approach that are interested, that might want to share their personal wealth, have earned that wealth through the construction industry, through development. Before they invest, they want to see that you have a real project. They want to see big equipment up there moving Earth. We have that now. That is really encouraging. The design on the enclosure is moving ahead. I showed you the 4 steps. The first one was hard rock excavation. Now the next 4 in the timeline for those running through 2020. Okay. And this bullet here, we now are working with TMT and NOAO, National Optical Astronomical Observatory, to get a strong ranking in the decadal survey, which is critical to extracting significant dollars from the U.S. government. We think that's going to be important to help us reach closure on the whole funding model. It might be critical, for example, to fund the last 2 or 3 instruments. Okay? So that's really good. I think we are in really good shape. And I will just close by the way I started. I want to thank João, I want to thank Claudia for making it possible for me to come to your marvelous city and your fantastic country, to meet all of you, and to say again how excited I am about this project, and to thank all the people in Brazil that are contributing to it with your knowledge and your background. A lot of young faces out there, right? You are the ones that are going to be using this. And so this is your future, and I look forward, probably from the vast beyond, to seeing what you do with it in 30 years. So thank you for having me. Okay, that's about right.
Okay, thank you. We have time for questions. Yeah.
Let's go back several years when you started this project. If you had to grade the major uncertainties back a few years ago, what would you say were let's say, the most important uncertainties, technological, operational, management, or financial?
Yeah, so it's a great question. If you look back a decade, what would the greatest uncertainties be? I think the first one that came to people's mind, and that was why they started early, was can you polish a mirror, an off-axis mirror? Never been done before with an 8.4 meter mirror. And that took a long time to do at the University of Arizona. It took years and years to get that done. Okay? Now the algorithm is working. You could see it's progressing more rapidly than we anticipated. So that would be number one. The second one, I think, would be, well, can we get enough organizations interested to provide the scientific and engineering expertise and the financial underpinning? They didn't have to guarantee that they could do it all, but you have to guarantee that you have a route to success. Right? People and organizations want to be part of a success. And so as you reduce the risk, you get more people jumping on and joining you. And so they had to structure the credits and the partnership in a way that rewarded organizations that came in early. So I think the technical risk of the mirror, the attracting the talent and minimizing the financial risk, which we still have all of these, right? And then the other questions come up over time. You have these mirrors, there are gaps between the mirrors. How do you ensure that the wavefront is phased correctly across the mirrors when you have this gap? We think we've solved that. Okay? That was a big one. We'll still have challenges. How do we get adaptive optics going with 7 different mirrors? Okay? But the big ones, I think, early on were polishing the mirror, getting the partnership, and setting up a partnership that rewarded taking risk, but also allowed for new partners to come in. We're talking with a number of other institutions about joining, and without naming names, I can tell you 2 of them said to me, when you got Arizona State to join, the first new member in years and years and years, when you got Arizona State to join, that sent a good message. That allows me to go to my president, my leadership, and say, look, if they can do it, so can we.
More questions?
What fraction of the costs are being covered by private donors?
So far, a very small amount. You bring in a couple million here, a couple million there. The 520 million that we have from the founders, I would say 500 of that has probably come, well, see, a lot of times the private donors give it to the university who then forwards it to us. So, for example, we have 2 mirrors that were named after a couple, the Mitchells, and they gave, what, 35 million? So do I count that as private, or do I count that as credit for Texas A&M and Smithsonian, Carnegie, pardon, thank you. I think if you think about the total cost, maybe 1.3 billion. Okay? You've got 500 million. I'm just very open about this, aren't I? You've got 500 million, that is 520 commitment by the founders, okay? We're looking for another 350, 400 million from the National Science Foundation. We may have some new partners, maybe another 100 million, and then we expect, say, 300 million or so from private donors. We've really ratcheted that effort up with the arrival of Jennifer, what, almost 1 year ago today, right? Before, it had been handled by the individual universities. You know, in the States, universities raise a lot of money from their alumni, from their fans of the university. Maybe they give to the football stadium, maybe they give to the business school, the medical school. So last year Harvard raised $1.6 billion, okay, in money coming in. And so previously this effort was centered in the partners, in the founders, okay? But now we find that to go to the next level, to get gifts of 10 to the 8th, 10 to the 9th dollars, you need to have a cooperative effect, and that's where Jennifer comes into play. So some of these enormously wealthy people, that the numbers don't even compute, right? I mean, somebody is worth $100 billion. The approach to them is viable because they are connected to more than one of our partners. And so that's the collective approach we're taking now. And takes a while to build this infrastructure, as any university in the States would tell you. But I'm very optimistic about 3 or 4 10 to the 8th gifts that are ready to close. So that'll be an interesting test to see. And as I said, the closer you get, the more people want to be part of it, right? But if you give me $1 3 years from now, that $1 doesn't buy you as much observing time as the $1 that you gave me 3 years ago. That's the model that the founders set up.
More questions? Augusto?
Augusto.
Robert, about the money for science, say, when you approach the private donors, they give you the money because of what do you sell to them, and if they have a discount in taxes, this is important
Yes.
or not.
Yes.
And the second thing about the money, you guys made a very good step forward, having TMT together.
Yeah.
So I don't understand very well what this means for NSF. So
Yeah.
you give more for the same amount of money they give, or you offer a cheaper, because they will need to fund both. I don't know what
Yep.
they will fund.
So
You guys will get something that makes some rationality and use the same amount of money to do more things.
Yeah.
So why they will be more interested in funding two instead of
Okay, so this is a really deep and multi-layered question, thank you, about how the U.S. government funds science and its role now with the 2 telescopes. First of all, the NSF has said we're not going to pick one over the other. They're both good projects. They're both U.S. institutions. In fact, TMT is in the U.S., in Hawaii. GMT has more U.S. institutions involved than TMT. So we're not going to choose. You have to come together. If you want us to support you, you have to come together. So we're finally coming together and talking about this. And each of us, TMT and GMT, is being very clear that we have certain obligations to our partners. There are certain governance structures that we have to honor. But we feel we can do that within the context of the NSF funding, let's say, I don't know, 350 million as 25%, or 400 million as 25% of the total cost, and getting 25% of the observing time. Okay? That's what they would like to do, have 25% of the observing time on both telescopes for the U.S. community. So if you're at the University of North Dakota and you're not a partner, you would still be able, through a competitive time allocation committee, to get some time on one or both of these telescopes. Okay? We have the space to do that. We haven't committed 100% of the time on the telescope to our founders because we haven't raised 100% of the dollars. So the math will get sticky. Actually, it's probably the arithmetic will get sticky, but I think it can be done. Now, the process for doing that, we're actually in a favorable situation now because the director of the National Science Foundation is France Cordova, an astronomer, someone I've known for ages. In fact, I was her reference for many of the jobs she got. Okay. The director of the broad math and physical sciences directorate that includes astronomy and math and physics and chemistry, Ann Kinney, she is an astronomer. And of course, the head of the astronomy division, Richard Green, is an astronomer from the University of Arizona. So we have a lineup in the National Science Foundation that's very fortuitous in that they understand the vocabulary that all of you speak. Okay? But they have to justify this based on the decadal survey. That's what astronomers have set up. The astronomy community is saying this is our top priority. If they say the top priority are the ELTs, the extremely large telescopes, then that releases the NSF to provide these funds. The timing on this is really critical. We will have to complete our proposal to the decadal survey, we being GMT, TMT, sometime by next summer. And shortly thereafter, at about the same time, the two of us will put a proposal to the NSF for $800 million. That's a big number to the NSF. It's not a big number to NASA, but that's a big number to the NSF. So all of this is in a compressed timeline. It's this working group that you saw with Claudia on it, with Pat, with Rebecca, and so forth. They're the ones that are moving this forward and are being very aware of the unique commitments we have, just as TMT has unique commitments. Theirs are more complicated. They have a country called China as a partner. Whatever you feel about China, the current view in our executive branch is not favorable. And so how do they work that? How do they work technology transfer through TMT to China? I'm glad that's not my problem. I used to deal a lot with technology transfer. So that's the NSF situation. Their goal is to give us sufficient money that within our model, they could award 25% of the time. And I think that's possible. It's not simple, but none of this is simple. Now, you also had a question about the private donations, I think. And there, private donors give for a variety of reasons. You think you're going to get out of this, but I'm going to call on you. Sometimes they just love the institution, and they go to the president, and they say, what's your highest priority? I was sitting at a spring training baseball game one time, and the owner of one of the Major League Baseball teams, the California Angels, Artie Moreno, came up to me and he said, here, I like what you're doing. And he gave me a check for $250,000 to just do what I wanted to do. It was the easiest money I'd ever raised. Okay? Now, of course, that isn't a lot of money for us, $250,000, but he just liked the program and he took the initiative. A lot of times they do it because they want their name on something. Right? So you've set up a number of naming opportunities. If you want to name the telescope mount, is that 80 or 100? 80 $80 million to name the telescope mount. Okay? The surprising thing are there are people out there that have this kind of money. Okay? It's just, we know a lot of them personally, and you want to say anything about why people give to their alma mater? Zhao has a microphone that you can use.
Goodness. Well, Robert, you covered quite a bit, but I don't know if I could really add much, but I think as Robert has said, it's various motivations. Often we find with our high net worth individuals, as Robert mentioned, they have a connection to not just one university that they may have a degree from, but maybe their kids went to Texas A&M and they went to Harvard, and they've always loved what's going on at the University of Arizona at the Mirror Lab. or we find people that are extremely wealthy and they may have a background in cosmology or physics. So you get these extremely wealthy people. We wish there were more of them, but at the very top of a pyramid that are quite intellectual. They care about science. They're disturbed by what's going on in the U.S. with sort of the war on science that we hear a bit about. And they want to make a contribution privately to a project like this. There are challenges to this kind of work. And I would say the number one challenge, stating the obvious, is the amount of money we need to raise. When some philanthropists look at all the problems in the world, and maybe their millions of dollars could have more impact here on Earth versus looking forward to the universe. However, one of the things we emphasize with donors throughout history, mankind has made these amazing leaps through technology. And if we stop pushing boundaries, what will become of our society? So it's an important thing to emphasize. We look to people that ask these esoteric questions. Where did we come from? What is in the future? We find that some of our high net worth individuals are obsessed with the search for life, which certainly there will be many missions of GMT, but this is one that captivates folks. So we talk a lot about that in conversations. So this is a new era for GMT in terms of really emphasizing the private fundraising, and beyond what the partners are doing, Robert and I are looking to augment that good work already with perhaps corporate, some other individual opportunities. So,
You want to mention the SPA meeting you went to recently?
I'm sorry.
The Science Philanthropy Alliance?
Oh, yes. So we recently, thank you, Robert, briefly, great organization that Robert was involved with in a previous position when he was president of Research Corporation in Tucson. Another organization called the Science Philanthropy Alliance had an event in Chicago. I think it's been about 4 weeks ago. And they had opportunity from U.S.-based foundations that are focused purely on science. And these have endowments that are, would we say, $1 billion endowment, Robert?
Yes.
Yes. So all of the representatives, I think there were 12 there, are directors of foundations with $1 billion endowments. They're spending between 10 and 20 million a year on science. Now, much of it is in biomedical, but it was a great opportunity. They had flash presentations of what they're doing, opportunities for future giving, and then people like me all rushed over to them after their presentations. But it was a fantastic dialogue, and also in attendance were Vice Provost for Research. So it was a really great opportunity for GMT, not only to get some face time with the foundations, but to integrate with potential new partners, U.S. universities that are intrigued by GMT. Maybe there are some faculty champions of GMT, but it allowed me to integrate with the fundraisers at some of these institutions, get them excited, explain our model, talk shop with them, and just keep these relationships going. So I think this this position, of course I'm going to say this because it's my job, but I think it's an important role to, as Robert was saying, to coordinate and emphasize and promote GMT.
Thank you.
Yep. And the capstone at that meeting was a discussion by Walter Massey, the chair of our board, along with Buell Januzzi, one of our board members and astronomer. And they were presenting the GMT to all of these foundations. And TMT also was there to present in tandem. And Jennifer very directly pointed out in an email that we had the alpha team there. We were much more prepared. We were ready to go. Walter Massey did a beautiful job. So it's getting in front of these individuals, many of these foundation presidents I've known for a long time. And it's all part and parcel as the technical progress continues to be just outstanding. That gives us the substance and the leverage we need to move ahead.
More questions? Okay, if not, let's thank our speaker again.
Well, Well, and again, thank you for the hospitality here. This is just a marvelous visit to a great city and a great country, so thank you for having us.
I would like to thank all of you for coming here, and now we'll have a coffee break, and I will invite you all for the coffee break.
I'm trying to figure out how to turn.